Picture this. You've got your incredibly sophisticated, highly intelligent AI assistant, the one you rely on for complex data analysis, intense reasoning, maybe even critical health triage. Now, imagine it completely breaking down, essentially turning into a useless brick, the exact second you lose Wi-Fi or step out of cellular range. That dependency on constant, unbroken connectivity, it's really the Achilles heel of modern artificial intelligence. So today, we're diving into a genuinely fascinating research project centered around a concept called teacher-healed quantization. This is a highly rigorous, methodically documented attempt to finally sever that cord and free capable AI from the cloud altogether. Here is our roadmap for this explainer. We'll be covering 1. AI's cloud problem. 2. The North Star equation. 3. Rigor and the imposter. 4. Shrinking the model. And 5. Real-world translation.
Let's start with Section 1, AI's cloud problem, the connectivity barrier.
Right out of the gate, the researchers highlight a massive barrier. Our absolute best, most capable AI systems are just too big, too memory-intensive, and way too power-hungry to run on commodity hardware or mobile platforms. They demand specialized accelerators and huge amounts of energy, which means if you're in an offline environment, a privacy-restricted zone, or just holding a standard smartphone, you are completely cut off from top-tier AI. Moving to Section 2, the North Star equation, capability per EDF. This brings us to the core theoretical framework the researchers developed to solve this exact bottleneck. But first, we need to clearly define the specific intervention they're using, which is called quantization. Think of this as the science of shrinking an AI model's digital footprint without accidentally breaking its brain. Technically, it involves taking a model that stores its weights in high-precision 32-bit numbers, known as FP32, and aggressively rounding them down to 8-bit integers, or INT8. It's kind of like taking an ultra-high-resolution photograph and compressing it. The file size drops dramatically, but the real challenge is making sure the picture doesn't just become an unrecognizable blur. And that leads us to the North Star of this entire project, which revolves around optimizing for a metric they call CPEF. That stands for Capability per Effective Deployment Footprint. You see, they aren't just trying to make a tiny file, they are carefully balancing the useful functional performance retained by the model, stuff like its accuracy and robustness, divided by the physical resources it actually consumes to run, like its serialized size, peak memory, latency, and energy. It is essentially the ultimate scale of AI efficiency. Section 3, Rigor and the Imposter, the fail-closed system. Now, shrinking an AI while keeping that perfect balance is incredibly difficult. To prove just how hard it is, there's actually a dramatic scientific detective story pulled right from the researchers' own experiment logs. Early in their INT8 quantization stage, their strict automated smoke gates caught an imposter. What happened was a mismatched PyTorch environment tried to silently pass off a full-size, uncompressed FP32 model as a successfully quantized INT8 result. In a lot of standard development setups, an error like this might have just slipped through, leading to completely false claims of perfect accuracy. But their system was brilliantly designed to fail closed, meaning it safely rejected the imposter and immediately halted the experiment. The crucial takeaway here is summarized perfectly by the researchers themselves in this quote: "A script completing successfully does not prove that quantization occurred." This level of scientific rigor is absolutely critical because their fail-closed system ensures we can inherently trust their eventual data. They demand actual proof through physical artifact changes, not just a green checkmark popping up in a terminal window. Plus, they fully recognize that simply making a file smaller is really just a software engineering victory. Theoretical compression doesn't independently prove real-world deployability. You could have a tiny file, but if it runs on unsupported hardware, it might actually be slower and drain way more battery than the original massive model. True success has to be measured across peak RAM, latency, and energy proxy on actual physical hardware. Section 4, Shrinking the Model, Baseline Results. Okay, now that we know their methodology is rock solid, let's look at the actual performance difference of shrinking their baseline model. For context, they used a dense FP32 ResNet 18 model trained on the CIFAR 10 dataset. The original FP32 baseline achieved 93.81% clean test accuracy. Get this, the compressed INT8 model achieved 93.82%. Out of 10,000 observations, the smaller INT8 model literally made exactly one more correct prediction than its massive baseline counterpart, proving that aggregate clean data capability was totally preserved. And why is that tiny plus 0.01% difference so spectacular? Because it translates to an absolutely staggering 74.83% reduction in deployable size. They shrunk the model to nearly a quarter of its original footprint, with virtually zero immediate loss in clean data accuracy. Shrinking the model's deployable boundary from 42.7 megabytes down to just 10.7 megabytes is a gigantic leap toward true edge computing. We're talking about a model that can easily be loaded into the working memory of your standard mobile phone or even a cheap embedded sensor, while retaining all the aggregate predictive power of its much larger parent. And finally, Section 5, Real-World Translation, Offline Resilience. So, what does this actually mean for the real world? And more importantly, what happens if rigorous testing reveals that this extreme compression eventually damages the AI's complex reasoning when it faces noisy environments? Well, this is exactly where the namesake of the research comes into play. If capability damage is found later down the line, the researchers have scheduled a teacher healing phase. It's a brilliant intervention where a much larger, high-capability ResNet 50 model, acting as the teacher, intervenes to help the compressed INT8 student recover its lost knowledge through calibrated distillation. It's essentially sending the compressed model to an expert tutor to patch up any specific blind spots caused by the quantization process. The researchers are also being very clear not to take a premature victory lap. We have to remember that while aggregate clean accuracy is preserved right now, true statistical equivalence is still pending evaluation. A model might look totally flawless in a sterile lab test, but true quality testing requires evaluating how it handles real-world chaos like noise, blur, or weather effects, which they plan to test using a corrupted dataset called CIFAR-10C. But let's look out at the horizon for a second. Ultimately, bringing this level of preserved AI capability down to a tiny resource-light footprint entirely unlocks offline AI for highly critical scenarios. Imagine edge medical triage devices or privacy-sensitive medical imaging right there in a remote clinic. You simply cannot wait for a cloud connection when lives are literally on the line, and you definitely cannot send HIPAA-sensitive data to a centralized server. This research provides the exact zero-latency offline resilience required for those high-stakes deployments. And that leaves us with a pretty powerful final thought to take away from this explainer. The era of AI being hopelessly chained to massive, energy-hungry server farms is ending. So I'll leave you to ponder this. When expert AI can finally operate flawlessly right in the palm of your hand without ever needing an internet connection, what industry is going to be disrupted next?